Okay, good evening everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I was last day, and I was talking about binary search trees. Now recall that these are proper binary trees. That means that all the internal nodes have exactly 2 children. But keep in mind, there's also leaf nodes as well. And the way I represent the binary search trees is I have these leaf nodes that don't have any records in them. But I also have these internal nodes. The internal nodes have records in them. In my pictures, I usually just draw the keys for them. So, that being said, I want to pick up from where I was last day. We started talking about operations for our binary search trees. We talked about get. We talked about computing the smallest record. But now I want to talk about some of the other operations. Now, the last 2 I want to talk about first are interesting because they mutate the tree. They modify the tree's structure. So what does that mean? That means if I were to do, for example, a put operation, say in this case, recall that that means that I'm going to have to include a new record, possibly in the dictionary. So in the context of a binary search tree, I have to have some way of being able to detect if there's a duplicate or not. Likewise, I have to have some mechanism for inserting it into the tree very easily, while I still maintain all of the properties of a binary search tree. So remember, a binary search tree, like I said, it's a proper binary tree, but it has also one additional property. Does anybody remember what that property is? It's very easy to remember. It has a name that's pretty much based off the name of what we're looking at. There's a property that it has. What's its name? It's funny because it's literally, I gave it a name that's very much like the name of the data structure. Yeah, the binary search tree property, or the BST property. So remember, that means that if I look at any one node, any one of the internal nodes here, if I look at any one of them, if I look at the left subtree, all of the keys of the records in any one of the nodes in the left subtree have to be less than mine. Any one that's in the right subtree has to be greater than mine. And this is true for every one of the nodes in this tree. So please keep that in mind, because as we modify the data structure, we need to make sure we maintain this property. It's very important. If we don't maintain this property, it means that we can possibly destroy the BST property, meaning it's no longer a binary search tree, which could be a bit of a problem, right? So the one thing I want you to keep in mind when we look at a lot of these operations we do with our data structures, when we look at this, we need to be a bit careful. We need to make sure that whenever I make a modification to the data structure, I have to make sure that the binary search tree property is still maintained before and after an operation occurs. So let's see. What does 7 have? Has 2 and 1 child only. So remember, it has exactly 2 children. One of them happens to be an internal node. So it's okay if this happens in a binary search tree. Just remember that these are children. This is a node, that's a node, this is just an internal node. Internal nodes have records in them. That's how we defined it the other day. So anyways, I want to talk about some of these operations. So I want to first start off with put. So remember, like I mentioned last day, I'm going to give variants of the operation so you can easily modify the algorithms I'm going to give you so that they behave the way we'd expect put, get, remove to operate with a dictionary. In fact, you can look at each one of them just like recursive methods or potentially subroutines that your algorithm would use for get, put, and remove. So if I had a put method or member function, it would call the algorithm I'm going to have here for put. But keep in mind that some of them are going to be recursive, some aren't. No. If I get smallest here, it gives me 2, right? Remember, the whole idea is we went all the way down to the left, and I get its parent. That's what we did last day. But anyways, I want to talk about put. So, remember that we want to use this binary search tree property to our advantage. So if I want to put in a record at 12, so I want the key to be 12, there's something that's nice that I know about the binary search tree. It's that I know where it should be, right? That's the one thing that is really nice. So one thing I want you to notice is that we have a way of finding a record with a key K in the binary search tree, right? Remember I gave you get last time. So get will tell me a node where that record should be, right? So there's two possibilities, right? So it's either going to get me a leaf node. So if it gives me a leaf node, if I use get, so it's either going to be a leaf node, meaning we're at a leaf node. If there's a leaf node, that means simply that means that there is no duplicate, right? We didn't run into a duplicate, because if we use get and we encountered that record somewhere along our venture down to the leaf nodes, that means that we found another record with the exact same key, right? So that's one possibility. The other one is I end up getting I get an internal node. So if I get an internal node, that means that there's a duplicate, meaning that I shouldn't perform the insertion. So these are our two possibilities, right? But the great thing is about a binary search tree is I'm able to determine which of these two cases occur. One happens when it's a leaf node, meaning that it's safe to perform the insertion. But the great thing is that it puts me exactly where I need to be. Or it's an internal node. It'll tell me, hey, look, there's already a record with this key in it. So in this case, if I were to attempt to put in, let's say for example, instead of 12, I put 11. If I tried to put a new record in with key 11, I would go right, then I would go left, and I would see 11, and I'd say, okay, well, that's an internal node, right? So I know that's going to be a duplicate record. So we know right away that this will give us a nice, easy way of doing this. But there's another part of this, is how exactly do I insert data into this binary search tree? Now, you might recall from the other day, I mentioned that when we have our binary search tree, when it's initially empty, we begin with just a leaf node. So we just start off with a leaf node if it's empty. Whenever I want to perform my put operation, what I do is I just simply perform the process we used for get. So remember, get will tell me, okay, if I'm going to attempt to find a record with key 12. So I know that it is indeed bigger than 10, right? Because 12 is bigger than 10. It goes left because 12 is less than 13. And naturally, 12 is larger than 11, right? So I just go left and right just like I did last time. So I'm using get, so I use get, and I find I'm at this node right here. So this is the node that I would get. So the question is, what exactly do we do at this node? Well, here's the great part. It's a leaf node, and leaf nodes don't have any data in them. So I can just simply create so I can use this node, and I'm going to put my data in there, and I just create two leaf nodes. So all I have to do now is I just simply take this leaf node, and I'm just going to inject the data that I want. So I just put in 12, and I create two leaf nodes as children. So this would be how I could insert directly into our binary search tree. But remember, have I violated anything about the binary search tree property by doing this? Can anybody see any problems with what I did? There doesn't seem to be any issues, right? Because you'll notice that exactly it's going to maintain the same properties that you would expect. Because the way I went down the tree, I went left, right, left, right. I found the appropriate spot where 12 should have been, right? That's the important bit. So when I put 12 right here, it's okay, because notice that 12 is less than 13, and that was because I went left here. That guarantees that we're okay. So notice that when I do this insertion like this, we're perfectly fine. Now, just as a remark, like I said, if you start off with an empty binary search tree, when you put a put operation like this, it would just simply turn this leaf node it'll just put the data inside of this node, then you'd create two leaf children, just like I did right here. So I want to show you just the algorithm that I have here for our put operation. So what I'll do is I give you a root, I give you a key, and I give you some data. So keep in mind that the algorithm I'm going to give you just tells you if you should if the insertion happened or not. When it fails to get an insertion occurring, that simply means that, oh yeah, I better throw an exception, or there might be something I have to do. If I follow the dictionary ADT to a T, I'd have to throw some error, right? I were going to report an error, but notice that here I'm just giving you the bits and pieces so that if you were to call this, it will tell you if the insertion happened or not. So I first start off by using get, and this will give me the node where I need to perform the insertion if it's possible. Now, as I said earlier, if P is an internal node, then you know right away you have a duplicate that you're dealing with. So you have a duplicate key. That means you're going to return false. You don't perform the insertion. Otherwise, we assign the key and the data of the node that we're at, because remember, this leaf node, what was a leaf node, has the ability to take in a key and data. It just has no data or key right now. So I just put it in there, and then I create two leaf nodes and set them as the children of P, just like I did here. So notice how I have two new leaf nodes. I just created those and I made them the children of the node that I performed the insertion at. And then I just return true. Isn't that nice? So notice that I'm using get to help me perform this process. So a very natural question is, okay, so what's the worst case time complexity here? So let's look at that. So the first thing you'll notice right away is there seems to be kind of like two big parts to this whole thing. What did K and D do? It's a dictionary, remember? It has key and has a key and value pair, right? So data is just the value of the record. So I have these two parts. So I have get. So remember, get we established the other day takes big O of the height, right? So we know that this is going to take, this first part takes big O of the height. And all of this. So determining if a node's internal or not, well, I could do that in constant number of operations. I could assign this for the constant number of operations, constant number of operations, constant number of operations, because I create two leaves. Returning true, constant number of operations. All of this is some constant number of operations, just to keep it brief. So if I have a constant number of operations plus something involving the height, which one wins out in terms of big O? Constant number of operations or the height? It's the height, exactly. So in this case, so if you're looking for a more careful explanation, I have one in the notes. But the time complexity for this is big O of the height, just like get was, just like smallest. So are there any questions about put before we proceed to talk about remove? So we've seen so far how we can be performing insertions into the binary search tree, such that we maintain all the properties of the binary search tree. But the question is, what do we do how do we remove things from the binary search tree? That's the interesting, I would argue that's probably the trickier of the two operations. So if we're okay, give me two thumbs up if we're okay. Give me two thumbs up if we're okay to proceed. Okay, so let's talk about remove. Because this is the one, at first, it'll look a lot, this is very nice and elegant, right? I just use the properties of the binary search tree to know exactly where I need to place things. It's wonderful. It's very wonderful. But the thing is, when I do removals, remember, I still have to maintain the binary search tree property. But it might not be as simple as just going down the tree and finding it, right? And just saying, I'm going to get rid of this. So there's going to be two cases here that you have to be very mindful of. So in fact, I'm actually kind of tempted here to draw a picture just to help indicate these two cases for us. So if I'm just going to do a little doodle off to the side here to make this a little easier for us to play around with. That's 7. We'll put 2 in here. And then we'll put 3 in right here. So I'm just drawing the same tree I have over there. So 16 has leaf nodes. Actually, let's just go all born in this. Let's put 11 here and 12 because I have that over there. So this is the same tree I just drew a moment ago. If you find yourself doodling this out, I'm just drawing a little smaller because I already drew it out once before. Okay. So, suppose I gave you this binary search tree, the same one I have over there. Now, if I wanted to attempt to do a removal, I want to do a remove operation. So I want to, say, for example, so when I do remove, remember, I give you a key, and I would like to remove the record that has that given key. So suppose that, for example, I look at, say, 3. If I want to remove 3, does anyone have any ideas of what I might try to do? So suppose that I was able to get to 3. Any suggestions of what I should do? So if I have that node with a 3 in it, any ideas what I should try doing? Yeah, so notice that you could just get rid of it, right? Exactly. So this right here is not very interesting, right? Like, there's nothing interesting going on with this case. I could just easily just replace this with a leaf node, and it'd be good as gone, right? Notice that's very similar for the case when if I were to try to remove 12 or 16. But there's other cases that are also kind of similar to this. Another one is, suppose that I looked at trying to remove 2 from here. If I attempt to remove 2, for example. So if I attempt to remove 2, notice that one of its children, at least one of them, is a leaf node. So if I were to attempt to remove 2 here, notice that I can easily have just moved, almost like shifted this up. Like I took this like a piece of paper and I moved it up like this, or I took 3 and I just plopped it up here. Would I be violating any properties if I just took this, what I have right here, and I just kind of just copied it and pasted it on top of here and just got rid of whatever's here? Like, it doesn't seem to violate any binary search tree properties, right? So this is what we would refer to as the easy case that I've referred to as case 1. So notice here that if I'm, say, for example, deleting at a given node P, if I have at least one child that is a leaf, notice that if I have at least one of them that's a leaf, keep in mind this also falls into the case where you have 2 children that are leaves. So all you would do is you can identify one of the children as C, so the one that is the leaf node. So there might be more than one. You could just pick whichever one if there's 2 of them. Then whatever there is, there's the other child. I'm going to refer to this as C prime. And the idea is that I want to get rid of P. So remember, this is a leaf node, right? It has no data in it. So if I were to, for example, just like slide this up, just like imagine this is what I have right here. If I just slide this up to right here, you'd see that it makes no difference from a binary search tree perspective. I know I'm talking from the perspective of the binary search tree, like it has some sort of sentience. I have no idea. I'm just having fun with you. So notice here that now all I have to do is I could just simply just pull that out. I could just shift this whole part up, and now I could just make P prime, which is the parent of P, I could just make that the parent of C prime now. Just likewise, P prime's child on the left in my picture here would be C prime. So all I do is I just shuffle it up. So you're going to see that this is actually the easy case. This is the easy case. So if I have this property, I could guarantee you I just have to shuffle this over by just simply just kind of knocking this out, and then I move this up here. That's all I do. But all it is just pointer adjustments. That's it. It's really nice and simple. However, there's this possibility, if there aren't any children that are leaf nodes, there's a possibility that is not going to be as simple as doing this. Instead, I have to consider the fact that both of the children might be internal nodes. So, we're going to try to pull out our favorite friend, the binary search tree property, to figure out what we need to do. Or at least one way to accomplish the removal. So here's an idea. This is just me suggesting something. Is remember that if I wanted to, for example, say P right here has this record with a key of Z. And I wanted to find out what exactly I could place right here to ensure that the binary search tree property is maintained. There's going to be surely a node that I could, with its data in it, that I could replace with whatever Z is, so I could take whatever its data is, so I could find some node in this tree that I could replace whatever Z is with that to ensure that the binary search tree property is maintained. It's a very specific spot in this tree. There's at least one or two possible ways to obtain it, but I'm going to suggest one here. And it's actually reliant on something I showed you the other day. So I'll give you a tip. So since both of my children are internal nodes, that guarantees I have a left child and a right child that are both internal nodes. But I have an interesting suggestion. If you were to just simply consider the right child, I have a question. What would be if I were to go all the way left from this node and I went all the way down to this node I've labeled S? Does anybody have any ideas what that might be? Any guesses at all? So keep in mind that going left all the way might even just be this node itself. Yes, very good. It's the lowest one that's just above the Z value of the key for Z, right? So it's just whatever, it's what we call, we had a special name for this. It starts with an S. It's this thing we call it. It's like when I jump in the air, I have a victory. I say, oh, I have done success. So we have what we call the successor. Very good. See, I had to hurt everybody with my S's. That was terrible. Actually, I'm just joking around. So anyways, so now if I can get the successor, if I go down here all the way down to node S, perhaps I can grab whatever's the data here. I can copy that all the way up into here. So I get rid of whatever's here. I could just take that. I could rewrite this with whatever data's in here into there. And then if I just delete this, the question is if I can do that. Because here's an interesting observation. If I go all the way down my left like this, what was that? Do you remember we talked about doing this last day? What operation was that? So there's an algorithm that did that. Yeah, smallest, exactly. So all I do is I call smallest on my right child. I just go smallest, I go all the way down. But here's an interesting observation. Do you remember my picture from when we talked about smallest? It was that I have a leaf node on my left. There might be stuff on my right child here. But the point is that there's a left leaf node. There's a left leaf node. But if I wanted to, for example, get rid of this node, if I were to just say, hey, look, and I'm going to remove whatever this node is. Just get rid of it because now I've copied its data up over at P. If I do that, what of the two cases is this at node S? Is it case 1 or is it case 2 if I were to try to do a removal at this node? It's case 1, very good. Notice it's case 1 because it has at least one child that's a leaf. So notice that all I'm going to have to do once I copy its data up to here, because I'm allowed to do this because that is the successor of whatever data, the key that was in here. So that ensures that the binary search tree property is maintained. But if I get rid of this, then I ensure that, oh yeah, everything's okay. I don't have a duplicate key kicking around. So I'm just going to remove that, but I could just use case 1, right? Because case 1 guarantees me that I have at least one of these leaf nodes. And the reason why that's the case is because remember, when I do smallest, I go all the way down as far as I can down the left. And whatever node is located at the spot that is the parent of that left leaf node is whatever I get returned, right? So you know right away there's at least one leaf node. And that's how you know if I were to apply remove at S, for example, I can guarantee you that it's just going to fall into case 1, which is the easy case. So I want to show you an example of doing this. So why don't we head over here? Let's do an example, and then we'll write out the pseudocode. Okay. So let's do another example. I should have just left the tree here, but I'll draw it again. So I'm going to presume that I did the removal of 2. Yeah, so you're going to notice it's going to be kind of subtle what we're going to do with this. So just pay attention to this very carefully. So I'm going to draw out the following tree instead. Let's write out this tree. 11, 12, 16. I have my leaf nodes. Okay, so this is just the same tree I had before, with the exception I've deleted or removed the record with key 2 in it. So I'm going to perform a removal of 10 here. So I'm going to try to remove. So I'm going to remove from the root here. So I'm going to apply a remove operation from R. And I'm going to try to remove the record with key 10 in it. But you'll notice right away, it's the root itself that has that key, right? But both of these are internal nodes, so we have to be a bit careful, right? So here's an idea. So I'm going to walk through this step by step. So the first thing you'll notice is that if I go to my immediate right, and I go applying smallest, I can go all the way down furthest to my left, and notice that I have 11 right here. What I'm going to do is I'm going to say, okay, instead of having 10 here, so whatever the record was here, I'm going to hang on to that. I can return it afterwards if I'd like. I'm going to put 11 here, so I'm just going to copy that over. So I'm going to copy this data over to this node. And then I'm going to apply remove on this node here with the key of 11 right here. So the great thing is that this is case 1. And I have reason why I know that is there's at least one leaf node for this given node. And that means all I have to do is I just take whatever's here and I just slide it up, or if it was the other way around, I would just slide it up like that. So all I'm just going to do now is I simply take whatever I have here. So I'm just going to go, let's just get rid of that. And I imagine I move this up. Keep in mind that I'm just making it easier for us to see what's happening by doing this. So we copied 11 up there, and then I did the removal at 11. And now I've noticed that I've done the removal. And now notice that I have successfully removed the record with key 10. But it also satisfies the binary search tree property because I got the successor of whatever was at that node. That's how I ensure that this is going to be satisfying the binary search tree property. So you'll notice it's a little bit tricky at first, but really if you just think about it as, okay, when there's 2 internal nodes, I go right and I go left as far as I can to find whatever I should copy over into the node that I need to get the data and place it in so I maintain the binary search tree property. So are there any questions about the example so far? Because that's all remove is. But I'm going to write down the pseudocode for it. So if we're okay with this, I'm going to proceed to write out the pseudocode. And this is going to be a little bit more involved than the other one. So I'm just going to make it so it's either true or false again, like put, where if it's true, that means that the node with key K was removed, and false if it was not, meaning that I failed to remove it because I couldn't find it. Because remember, in our dictionary, if I fail to find the key that I want to remove, you're supposed to throw an error, right? So I'm going to do remove. I'm going to give you two parameters. So input is just going to be a root R of a binary search tree. And some key K. And for output, let's hope I can fit this all here. So let's do this. So true if node with K was removed. False otherwise. So like I said, you could easily modify this to make it so it actually returns back what exactly you removed. So I'm just giving you something that we could easily adapt to use in other purposes too, if you'd like. You'll see how I'm building all these bits and pieces for later. So like I said, these are very easy to modify. So if you say, Dan, well, it doesn't return the record, it's very easy to modify it. I'm just trying to show you how you could write it out, and you could easily modify it afterwards if you find yourself curious about it. So first, I apply get. So again, I use get to find the node that I want to get to, P. So I just use get like I did before. So I find the spot where I'm at. You know right away that there's nothing to remove if P is what kind of node? So what kind of node would P have to be to know that, oh yeah, it's not in the dictionary at all, if you think of it as a dictionary? Well, not null, not null. What kind of node would it be? A leaf node. Very good. I like the guess of null, because if, say, we're talking about the other binary search tree representation, it would be null. But in ours, it's leaf node. So it'll be a leaf node in our case. So if P is a leaf, then you just return false. So you know right away there's nothing you're going to accomplish here. Now we have the fun of this, and I'm pretty sure I'm going to have to write more of it over here. We'll see what happens. So first, I need to identify case 1 from case 2. I'm going to first start off by writing case 1 out. So if P has a child, C, that is a leaf, then you're going to do the following. So note that this is case 1 right here. So this is case 1. I'm just going to, this should be like right there, but I kind of ran out of space there. So this will be case 1, right? So first, I'm going to identify P prime just like in my picture. So P prime is going to be the parent, a parent of P. Then I'm going to identify the other child of P, because remember, I know that C is a leaf. So I need to know what the other child is, because it might be an internal node. It might be a leaf, might be an internal node. But I'm going to call that C prime. So C prime is going to be the other child of P. The other child of P. And now you might naturally ask, Dan, what happens if the removal is happening, for example, at the root of a tree? That's a very natural question. Yes, you'll have to update the root of the tree if that is the case. That's one case I did not tell you about, but I want to make sure it's here. So if P is the root, because it might be possible that I might actually be removing the actual root of the whole tree, I have to reassign what the root is. Remember, the root is an attribute of the binary search tree itself. Just like if you think of it like the head of a linked list. I need to make sure I update it if I delete off the head of the linked list. Same idea. So if P is the root, then we're going to make C prime the new root. So you're going to make sure to update what root is to be C prime. So lastly, otherwise, we're going to make C prime the child of P prime. Just like in my picture. So, like I said, you're just going to slide it up one level. So the other one just goes away. We don't need it anymore. And that's case 1 right here. So I'm just going to, okay, I'm going to fudge this a little bit. I'm going to move this up a little bit. So that will end the if statement here. Naturally, I have case 2. I'm going to write case 2 right here. I think this is the first time this term that I've had to write the pseudocode where it kind of goes up to the other side, so it always makes things fun when I have to do this. So otherwise, we're going to have case 2, and case 2 is much shorter to write out, is first I get this node S, like in my picture. So all I do is I apply smallest. So I use smallest on the right child. The right child of P. So you apply smallest to the right child of P, just like what we described. And then what you do is you copy the key data from S to P. Okay, I'm going to make this a little spaced out, otherwise it looks like it's saying stop. Let me write that a little bit wider. S to P. There we go. That's a little bit better. Otherwise it says stop, and that sounds a little bit confusing. Copy key data from S to P. So that's the copying step that I did. And then I just simply apply remove. So now I'm just going to apply remove to where I rooted at S. And then I just search for the key that is the key in S. And then lastly, I just return true. And regardless of these two right here. So note that this is technically a recursive call that's happening here. Just I'm recursively applying remove to the subtree rooted at the node S. And the thing that's nice about knowing S has a certain key in it, I know I could search right for it, right? How do we make so question, can you explain again how we make C prime the root in case 1? Sure. So suppose I had a tree that looked like this. Suppose that this is the root, and say this is node P. So what's possible is that if this is the child C, that's the leaf node, and its other child is C prime, if P is the root, and I attempted to remove whatever's here, you know that this has to move up like this, right? So we take whatever's here, we say, okay, this is going to go right up here, and I can just get rid of all of this, right? But the thing is I can't just simply do that, right? Because this is being pointed at by the root. So what I have to do, to be a bit careful about this, is I need to make sure that I reassign the root to be C prime. Just like if, for example, you're doing an insertion in a linked list at the front or the head of the linked list, I need to make sure I update the head of the linked list. Just like if I have the root of the binary search tree, I have to make sure I update the root. Does that clarify your question? Do you find this kind of helpful? Yeah, so it's one case you have to watch out for. So the one thing I got to point out is when you're implementing this, keep in mind that there might be possibilities where you're going to have to update the parent and the children appropriately. So when you see like the parent of P and so on, we make that the child of P, keep in mind that you also may have to update, say, the parent attribute or potentially other attributes of that given node. So some of those details, when I say make C prime the child of P prime, you may have to update those too. So that's what I'm sort of suppressing when I write out make C prime the child of P prime, for example. So just okay. So that's actually an interesting question. So there's a question is, why aren't we considering the left side? So I decided to pick the successor for the removals. I must note that you can also use the predecessor, technically speaking, for the removals, because you do have 2 children. So you can guarantee there's also the existence of what we call predecessor as well. So you can, technically speaking, redesign this remove algorithm so that it computes for case 2 the predecessor instead of the successor. But it makes things much easier for us to keep one convention. So in this class, I'm going to presume it's the successor that we get as opposed to the predecessor. Because if we've got to be very careful, because if we decide to start removing from one side or another side, it changes the way the tree might be drawn out, and it creates inconsistencies for what we're expecting to happen. But keep in mind, it will still technically work if you were to try to get the predecessor and you copied over what the predecessor's data is and into the wherever node you're trying to remove from, and you do the same steps here. That also works, but you have to be a bit careful because now you're not using smallest anymore. Now you're doing something else. But yeah, no. So let's talk about the time complexity here. So you notice that in our diagram, we thought about this very carefully, right? So notice that I have get here. Just like in the previous case, we know that get takes big O of the height, many operations. And now I have all of this. So I have if P is a leaf, then return false. And then I have if P has a child. So I have all of this. So if case 1, let's take a look at case 1 in this if statement first. Then we'll examine what happens with case 2. So we know right away that all of these things I'm doing right here, all are pointer adjustments. Sorry, I'm getting very excited here. I'm just like, oh man, this is amazing. So I'm just going through, notice that all of these are just me getting information about the nodes and I'm making pointer adjustments. That's all I'm doing here. There's a constant number of these pointer adjustments happening. So if I were to look at all of what I have here for this if statement and this first part of case 1, for everything I have right here, all of this can be thought of as a constant number of operations. Sorry, let me write that in black. It's some constant number of operations, right? So that's what's happening with all of that. But the question is, what happens with case 2? So in case 2, remember I call smallest. Now, the first thing you'll notice right away is that, okay, well, how long does smallest take? Can somebody tell me what does it take in terms of big O? It's involving the height, right? It's big O of the height. I'm just going to erase this one picture just to help me finish writing this up. So, you know right away, this right here, this step here is big O of the height. Then we have this copying. This can be done in a constant number of operations. But then there's this very strange one right here. This removal, it's a recursive call, but it's a little slick here. So notice that it's calling it recursively at S. So that's the node I'm going to perform the removal at. But we established earlier that that is happening at that's going to invoke case 1. But what did I say about case 1? How many operations does case 1 take right here? It's some constant number of operations, right? But remember, when I recursively apply this, it's going to do get, but get is literally going to be at that node. So notice that if you look at the number of operations, if you think about it from very specifically, we know exactly which node we want to remove, plus all of this takes a constant number of operations. This call here, you could just think of it as a constant number of operations. And even if I wanted to be generous, I could throw big O of the height there too if I really wanted to. So I will do that, even though technically speaking, it is still going to be some constant number of operations because I'm just removing at a node I'm already going to get to immediately in the search. So I'll just write big O of height because technically that is an asymptotic upper bound on the number of operations that occur there. And we know that this copying and this return here, these are some constant number of operations. So the easy answer is, what exactly is the time complexity for remove then? So we have big O of the height, we have some constant number of operations that happen, there's some big O of height happens there, big O of height happens there. But notice right away that we aren't going to keep repeatedly applying remove over and over again. It only happens once. So it may as well just be like if I copied everything here and placed it right here. Except for node S. So the time complexity in this case, what is it, everybody? It is big O of the height. Very good. Very good, very good. So notice that in this case, we have big O of the height. You're seeing a pattern here, right? That all the operations that we've been looking at, they all seem to be big O of the height. That's a nice feature about all of these operations with the binary search tree. Now, in the notes, I'm going to include an algorithm for the successor. I encourage you to take a look at it. So you notice that in our algorithm, we computed the successor in a very specific case. Where, remember, I always want to find the successor of a given node, and I knew exactly where it was because of the case it fell into for the removal. However, that sometimes isn't necessarily the case, and instead you either have the case that we just did here, or I work my way up the tree finding where I have the next immediate successor. So I want you to take a look at it in the notes. So take a look in the notes after class for the successor, which you can also do in big O of the height. So you can compute the successor more generally in a binary search tree using only big O of the height number of operations in the worst case. So that leads me to an interesting conundrum here. So actually, before I proceed, camera, stay there, stay there. Okay, very good. Are there any questions before we proceed? I want to shift gears to talking about something a little bit different, but are there any other questions about remove? Okay, so if we're doing okay, let's proceed over there. I want to talk about what we have, all these results that we derived. So we have all these nice results, or at least they seem that way. So they seem to all involve the height of the binary search tree, and I want to talk about this. Okay, so all the main operations we discussed So when I specifically mean that, I mean things like get, remove, put. I'm not referring to like the traversals. The traversals, they take linear time in the number of nodes, right? All of these, they take big O of h time, where h is the height of the tree. Now, the first thing that you should notice is that the height seems to be an interesting parameter for when we consider a binary search tree. But it's not really a robust one in the sense that I would like to have nice, efficient data structures in the way that we've talked about earlier. So the height itself is an interesting parameter when we discuss a binary search tree, but let me present to you how the height of the tree can vary. So the height of the tree can vary. So that's the first thing you need to know, is that the height of this tree can vary, which is quite natural if you think about it in terms of doing a whole bunch of insertions. So I'm going to show you two nice pictures. So I'm going to draw you a couple nice pictures. It's a little squeaky. So, this is an example of something called a balanced binary search tree. And its height is exactly equal to the ceiling, so you just round up whatever this result is, log base 2 of n plus 1 minus 1. That's what its height is for a balanced binary search tree. For our purposes, its height is big O of log n. That's the thing you should take away from this, is notice there's a logarithmic function in here. So you can see that the height of this tree is big O of log n. That's wonderful, because if you think about it, from all of those operations I told you about, if I can ensure the binary search tree looks something like this shape, something like this, that would guarantee that every one of the operations we talked about, doing get, put, and remove, for example, smallest, successor, all of these can be achieved in big O of log n time, which is better than all the other implementations we talked about, right? At least generally over all of them. The other ones sort of had trade-offs that are quite heavy, right? Where it's either it takes constant number of operations or it takes a linear number. And this, if I had a tree that looked much more like this, it doesn't have to look exactly like this, but something like this, where its height is big O of log n, then the question is, okay, so if I can achieve this, then it would be great if I can get that, because then that would guarantee me faster operations for all three of those, which is great. That's great. So there's a problem, though, is that binary search trees don't actually have this guarantee. So this is one drawback of a binary search tree that I want you to be aware of. So a binary search tree doesn't have to look like a balanced binary search tree. It can, in fact, look like a degenerated chain, which looks a lot like if I just took a linked list out and I said, hey, look, I'm going to attach a whole bunch of extra children to these. So notice here that this is also a binary search tree, assuming that all these keys maintain the binary search tree property, which is easily one you can construct. For example, you can easily take and you can insert a sequence of keys that all are in increasing order, for example. You can build a tree just like this one if you insert them in this kind of order. So it's not like these kind of trees aren't something you can run into. They're very easy to build sometimes. So the issue here is that if I look at the number of internal nodes, so all the internal nodes in the path, so all of these internal nodes are in this path. And to make it easier for you to see what could be the problem here, I'm just going to cover up one part of this. What does this remind you of? What kind of data structures does this remind you of? What does that remind you of if I get rid of all of these children on this one side? What does it look like? A linked list. Exactly. Exactly. So you know right away how long it takes to traverse through a linked list, right, in the worst case? You know it's going to be based on how many nodes I have in the linked list. So the question is, okay, so how bad is this? So notice that if I want to look at the height of this, so if I looked at the height h, the h is going to be at most the number of internal nodes. And if you counted up how many internal nodes there are in this, it's going to be exactly n minus 1 over 2. And that means that h here is actually going to be big O of n. So it means that you have sort of this thing going on where you can either end up with something that's nice like this, or it could potentially degrade into what I've drawn over there, where the operations all take linear time, where n is the number of nodes. So, well, the number of records, sorry, to be more precise. It's the number of records. So, anyways, so we often refer to this, by the way, this is sometimes people call this a degenerate BST. It's because the structure of it has broken down completely to a point where it just looks like a chain of nodes. So some of you already caught on to where I'm going with this. So we've talked about binary search trees, which you can easily implement using everything we've talked about. Now, what I would like to do is I want to address this fundamental issue that I've just shown you here. So you can take a binary search tree, you can implement it, but remember all of the operations for a general BST So for a binary search tree, the worst case time complexity of the operations discussed are big O of n. So we would like to be able to improve upon this. So we're going to address this issue. So binary search trees, you can totally implement them. All the algorithms I gave you will work regardless. We have to deal with the worst case time complexity being big O of n for get, put, and remove, for example, or smallest, for example. So what I would like to do is I would like to speed up this so I get a tree that looks much more like this. So one thing I would like to do is I would like to introduce you some way that maybe we can beef up the binary search tree. So I would like to make it so it goes, I want to make it look much more like a balanced binary search tree. Now it doesn't have to be exactly like one, but my goal is I would like to make it so that its height is big O of log n. If I can do that, then get, put, and remove all take big O of log n, for example. So we're going to specialize the binary search tree to try to get something like this. So I'm just going to give a couple definitions first. A tree is height balanced. It's height balanced if h, the height of the tree, is big O of log n. So that's the first thing I want you to be aware of. So what I'm going to do is I'm going to present you something we call a self-balancing tree. And the tree I'm going to present to you, so it's a type of binary search tree. It's called an AVL tree. So let me just make a couple notes about this. So we will now present a self-balancing binary search tree called an AVL tree. So this is going to be our main next topic we're chatting about here. Now you might ask what exactly this is, what AVL stands for. It's involving the authors of people that came up with this data structure. It's Adelson, Velsky, well, it's Addison, Velsky, and Landis, so there's two here. So that's where the AVL comes from. One of the authors' last name is Adelson Velsky, the other one's Landis. That's where AVL comes from. That's where its name is. It doesn't have any other functional name. It's just attributed to these people. And it was developed in the early 60s. So to give you perspective of where we are in the history of computer science, era 1962. This is when this tree was first presented, and all the theorems that were used to come up and derive all the analyses were done back then. So just be aware that data structures do evolve over time. There's a lot of work that's happened since then, but this is a nice classic data structure I want you to be aware of. So let's talk about AVL trees. So remember, the big reason why I'm introducing these to you is to address this issue with binary search trees. So binary search trees, they all work. All the algorithms I gave you will work perfectly fine. Just the problem is that I want to make it so that the height is height balanced. I want to make sure that the tree is height balanced. If I can guarantee that, then the height will always be big O of log n. So let's talk about AVL trees now. So I'm going to first define a couple of things. First, I need to define the notion of a height of a node. So it's going to be quite natural what the height of a node is. So you know how I consider a given node and I say, oh, the subtree is this node and all of its descendants, right? Well, that's essentially what it is. So what is the height of a node? The height of the subtree rooted at, and in fact, I'll say a node P, rooted at P. So it's just the maximum depth from, if I give you P as if that was the root, it'll tell me what its height is. So what I'm going to do first, so this is the first modification I'm going to make to the binary search tree. So we augment, so it means change or modify. So we augment a binary search tree to include in each node its height. So that's the first thing. So when I create a node, I'm going to presume that its height is 0 and 1 if it's an internal node. When I insert it, the algorithm will be developed so that it will appropriately set up this update if necessary. So, just assume when the node or a node is created, its height is 0. But as I mentioned, later on, the algorithm will be designed so that if it's an internal node, its height will be 1, because remember, the leaf nodes, if I have an internal node, what's its height? But if both of its children are leaf nodes. So just remember, if I had an internal node and both of its children are leaf nodes, what's the height of this node? If I call this P, what's its height? Well, so remember, it is the height of the subtree rooted at P. So notice that these are nodes. So the maximum depth of this tree is 1. So if I pick off any one of these two nodes, I ask how many ancestors it has. It has 1. So its height is 1 in this case. So when I give you the internal nodes in the process of this algorithm, these will be changed to 1 instead of being 0. So it's a very subtle detail. I made sure I noted it in the notes, but for our purposes, it won't matter too much at this stage. So what we're going to do is we're going to maintain these heights at every one of the nodes in the tree. That's one thing I'm going to do here. So that's the other part of this. So if we maintain the heights at all the nodes, we can update any node's height. So that's going to be one important detail for us, is maintaining these heights for every one of the nodes. So whenever we make modifications to the tree, we'll have to make sure we update the heights appropriately. So I gotta obviously give you an algorithm for doing this, but I'm going to make 2 presumptions that make this a little easier to play around with. So I'm just going to assume nodes can get or set the height using get height. So there's going to be a getter for get height and set height. So a setter. And I'm also going to presume that this set height is only called on internal nodes. So I'm going to presume that if I call set height, it's always going to be on an internal node. Because when I have a leaf node, its height is 0, right? That's not very interesting. You're going to see as we do modifications to the tree, I always want to update heights of internal nodes, not leaf nodes. Because those, I already know the leaf nodes, their heights are 0. So, I'm going to give you a quick algorithm for recomputing the height. So, remember, there's two things going on here. I'm going to maintain that all of the nodes have an extra attribute in them called its height. And the other detail is that I'm going to make sure that whenever I make modifications to the tree, I update whatever the height is. So as I'm building this tree, I'm going to maintain every one of the heights of the nodes. And you might ask, Dan, is there any drawback to doing this? Now, of course, the first one is that technically speaking, you are introducing more memory usage for the data structure by storing the height or any other attribute like it. But it's still going to be a constant amount of memory I'm using because it's just a number. And I do this for each one of the nodes. So if I think about it from a space complexity standpoint, it doesn't really do anything to add an extra attribute that's a constant number of them for each one of the nodes because the space is based on the number of nodes in the tree. So let's write out a quick algorithm. So I'm going to have an algorithm called recompute height. So I'd like to be able to call this on a node and update its height. And the great thing is that we actually know how to compute the height of a given node in a tree. We know how to do that. We've actually seen this earlier on just for general rooted trees. So we could do this even faster if we know that all the nodes have their heights in them. So updates the height of P. So I'm going to presume that P is going to be presumed to be an internal node when I do this. So, because remember, a leaf node doesn't have any children, right? But I'm going to presume it does. So, this is going to be one of the shortest algorithms in this course. So, hopefully you enjoy it. So, I'm going to go P, and I'm going to call set height on the node. So, if you're implementing this, it would be an arrow, probably. So, I have P, and I call set height on it. Now, we'll see if everybody remembers how to do this. So suppose I have a node here. Suppose that this is node P. And I know that it might has a left child and a right child. But one of these might be a leaf node, that's okay. But each of these has its own height, right? I can get their height by just calling get height on that one node. So the question I have for you is, how do I compute the height for P? Let's see if you remember this. So we actually see an algorithm that uses this formulation, just we don't have to use the algorithm anymore. Yeah, so you call get height on, so notice I have my children. I'm going to call get height on my two children, and then I'm going to add 1 to it, right? That's what remember our occurrence relation we came up with for computing the height of a tree? All I'm going to do is I'm just going to invoke it directly. So I'm just going to go 1 plus the max of, I'm going to get the left child of P, and then I'm going to call get height on it. Oh man, I'm starting to run out of space. I'm going to write it just below here. It's going to be the maximum of P, where I get the left child, and then I get its height, and P, where I get the right child, and I get its height. And that's it. That's the entire algorithm. Isn't that nice? So that's all there is to this algorithm. So the reason why this is so nice is because I'm maintaining the heights in all of the nodes. So if ever I want to update the height at a given node, I just inspect my two children and I could get the node's heights from those. And I just add 1 to it based on the definition of what the height is of the tree, which would just simply be the subtree rooted at P. So the natural thing you can see right here is that it just... Can somebody tell me what the time complexity of this algorithm is? What's the time complexity of computing this? Remember, it's very simple. It's constant, exactly. It's big O of 1. So the time complexity is this. So updating a height of a node is big O of 1, right? All I'm doing is I'm just using getters and setters. There's nothing else going on that's very interesting here. So you know right away this is really nice. So all I'm doing is I'm using a big O of 1 additional space, and I have big O of 1 time to update any one height. Now here's the thing that makes this a little bit tricky. We don't want to call this every single time I make a simple modification to the entire tree. Otherwise, what happens is it'll be very expensive for me to update the tree every time I make a small modification. Ideally, I would like to only update the height at specific nodes as I make modifications. Otherwise, what would be the time complexity of, say, for example, I do an insertion or a removal, if I had to update at every one of the nodes, the heights? Can somebody tell me what the time complexity of that would be, presuming that the time complexity of any one of those operations was something like big O of the height or big O of n? What would it be? Any ideas? Yeah, it's big O of n. So we want to avoid doing this. We don't want to update every one of the nodes. We don't want to do like an in-order traversal of the tree, for example, and update all their heights. We don't want to do this. That's expensive. So we do not need to compute the height of every node in the tree every time it changes. So that's one goal that we're going to have. This is a goal that we're going to achieve, is that so I don't want to go through the entire tree and update all their heights. That is expensive. So the last thing I want to do here today is define what an AVL tree is. So let's talk about what an AVL tree is, and that'll be the perfect place for me to stop here. So that when we come back, we can talk about some properties that AVL trees have, and start talking about how we could do some things with the AVL tree. Let me just switch markers here. This one's being a little bit funny for me. Okay. So let's define what an AVL tree is. So the first thing I have to do is I have to define what is called the height balance property. So the height balance property. So what it is, it looks like this. So I'm going to draw a picture and then I'll explain what it is. So suppose I have my two children that are internal nodes. And they have potentially descendants. So imagine I consider the heights at these two nodes. I call them HL and HR. What needs to happen at every one of the nodes is that the heights, so this is the height of the right child, this is the height of the left child of this one node. It has to be that HL minus HR, where I take the absolute value of this, has to be at most 1 for every node. So let me write this out in words. So for every internal node, actually every internal node, let's be a bit more precise, every internal node, P, the heights of the children, and this is why I like writing it out. It's much easier to understand if you're not familiar with this notation. The heights of the children differ by at most 1. So it means that they're allowed to have a little bit of freedom for how you lay them out, but the heights of any one of the nodes, if I pick any one node that's an internal node, if I inspect the height of the left subtree and the height of the right subtree, their heights can differ no more than by 1. So what an AVL tree is, simply, what an AVL tree is just simply a binary search tree that satisfies the height balance property. That's all an AVL tree is. So anyways, when we come back, we're going to see why for an AVL tree we'd like to have this height balance property. So when we come back, we'll derive why we might be interested in the so-called height balance property. So that being said, I want to say thank you very much and have yourself a beautiful evening. I'll see you later.